Yeah. Okay. So, so yeah, today we said we'll talk something about so errors, right? When you process something in a quantum setup, there will be some error, and this is actually a fundamental paradox. Why in quantum computation? Okay, so when you mm, perform some kind of quantum computation, meaning what? So you have to prepare a state. That's the first thing. Preparation of a state. Then some unitary matrix is the circuit. So unitary matrix, and then you have a measurement. So preparation here means you have a quantum register, let's say. Okay, so number of bits depending on whatever you can assume it like this. Okay, so and then unitary means something will happen. There is some kind of a procedure. Okay, so as I said earlier also, that even if we are using the icons, using wires and other things, okay, like logical bits and this and that, but this does not make any sense because there is no wire as such. Okay, but this is just a representation to mimic the everything like from the classical. If you want to do that, then we so people have invented this kind of icons for this kind of gates. But actually what is happening is you have this quantum register basically, and this quantum register has a particular state, and then something will act on this individual qubits or whatever it is, or maybe the entire state, something will act. So there is some kind of a procedure here. Okay, some kind of procedure. So this is what is the quantum circuit, and then you have to perform a measurement. This is what is happening here. Okay, whatever. Yeah. So yeah, so this is some kind of a circuit. I mean, realization of a circuit. I mean, you can say this kind of something which will use in order to implement experimentally, let's say the corresponding unitary transformation, and then you have this kind of a measurement. Now, when we are doing this, we said, what is the paradox here? That we want our qubits to be isolated perfectly from the environment, let's say. Okay, so whenever we are creating, because this is a sensitive thing. Okay, sensitive in a sense that, as we said, that if there is a small amount of disturbance, meaning a small amount of interaction with this with any other qubit or whatever it is. Okay, so whatever they are in the environment. Okay, so that may affect the state of this entire quantum register. So that's why we want this register to be, or the qubits, let's say, to be isolated from the environment. But again, we are saying we have to perform measurement. So there is a measurement device, like some apparatus is there, some measurement apparatus, but this is also external. So it is not internal. Okay. So because it is somehow it is there in the, let's say, in the quantum processor, it is somewhere there. So we want it to be isolated, as well as we want to use some kind of an external device which will which will do some kind of, like you have to, let's say these are photons, so it has to pass through some kind of a thing, so that you can have a sense of measurement. Okay, probably we have done this in quantum mechanics class. So this is so this is kind of a paradoxical, because we want to avoid that, but we actually have to do that. So once we do this kind of a thing, like, so there is a chance of interaction, and then the states here, let's say the psi is the state, there's a chance that psi can be, the state can be changed. Okay, and if the states can be changed, then there is a problem. So what happens this in classical computing? Classical computing, instead of this quantum state, we have a classical state. Let's say 0, 1, whatever it is. Now, if you want to do anything, like whether I want to know 0 or 1, this is perfectly all right. I can do that because this does not change my setup. So the measurement does not change the state itself. Okay. So, and even if there is a quantum channel, let's say, I mean, if you consider a quantum information processing, a classical information processing kind of a thing, like a communication system, you have to process this 0, 1 into from one part of the machine to another part of the machine. Okay, maybe there is a chance of error, maybe, and it can be modeled for using some kind of a channel. Okay, so like a binary symmetric channel. Okay, so there is a chance of error also, but in classical error correction, what happens if there is some error, like some bits are flipped, let's say from 0 to 1. So there is a procedure where you can see, you can perform some kind of measurements which will not do this, would not change the original state, let's say. Okay, so and somehow there can be some algorithms to rectify that error. Okay, this is literature. I mean, this is also hard in classical computation, but let us say we do not have this kind of a situation like where if I perform measurement, the state will change. But suppose I want to send, okay, we'll talk about that later maybe. So that the thing is, quantum, when you have a quantum register and want to perform some kind of a measurement, so that may affect the future state, like the next stage, whatever you want to do in a particular quantum computation. So the intended, the desired state may not reach to that particular stage, and there may be something which will go wrong and we may not get the desired result. Okay. And so maybe it will not follow the Schrodinger equation even because there is a problem with the state itself. There is some kind of error, and so that it will give you completely different dynamics. So that may also can happen. Now the question is, okay, so you have to design something, okay, which will support this infrastructure. That even if there is some kind of an error, okay, while you are processing some qubits, let's say, okay, apart from some kind of measurement, okay, whatever you are doing in order to implement some kind of a quantum computation, so there must be an infrastructure, okay, which will rectify that, okay, which will identify the error and it will rectify that. Okay, so basically there are two sources. I mean, I'll discuss basically two sources of, let's say, errors, what can happen. I mean, I'm just giving you a particular example, but it can happen in very many different ways. Okay, for example, you can say like this, there is a dissipation. Okay, dissipation means what happens? Suppose you are working with some kind of energy states. Okay, so suppose something, so there is an atom or something which has some excited state which you represent by 1, and suppose there is some lower energy state, let's say, which you represent by, let's say, 0. Okay, now what happens is, due to some kind of transition or let's say some kind of interaction, so what may happen is that this 1 can change to 0, because maybe suppose this state has released some emitted some kind of a photon, and energy became less, and then this is completely flipped. So this transform from 1 to 0, and that you do not know because you cannot measure it. Okay, so what happens, for example, in a particular case, let's say you are dealing with some state psi. I think you know about this no cloning theorem, right? Do you know about? You know about?
We cannot copy a qubit.
Yeah. So suppose we are doing this. We are using this. Okay, we are using this this particular state. Okay, in the computation, and I precisely do not know what are the values of A and B. I only know the values of mod A square and mod B square, let's say. The problem is, unless I measure it, I also do not have exactly what is the value of mod A square. So since I cannot clone it, I cannot, let's say, copy it. Copy is a bad word, in fact. Anyway, so let's say I cannot copy it. So then what will happen is I cannot perfectly create another state which will also be in a state psi unless I measure. But if you measure the psi, then the state will be destroyed. But what happens is, suppose this kind of a energy dissipation happens, and what happens is the 0, let's say A0 plus B1, okay, can change to some B0 plus some A1. Why? Because let's say there is some interaction, and this can be modeled as some application of this gate sigma x or not gate. Okay, sigma x are applied, so 0 is flipped to 1 and 1 is flipped to 0. So this kind of an error could happen when you are doing this. And if that is the thing, what happens, then this is called a bit flip error. So only one bit, 0 is flipped to 1 and 1 flipped to 0. So this is called a bit flip error. Okay, this may happen during computation. Okay, another example is which is called decoherence. Okay, so decoherence. So what happens is, instead of a bit flip, what can happen is that due to some interaction between the qubit and the environment, okay, that may change the state of the quantum memory or quantum memory register, quantum register, let's say. Okay, and what happens is, like, since the environment is I mean, environment space can be also thought of as a Hilbert space, because suppose there is a particle side by. Okay, so that is the environment in that case. And then what happened is this state, the original state which you had, which you want to process or perform some computation on this, that may get entangled with some state, let's say phi, which is environment, okay, which is in the environment. And then that's another problem. Okay, so your state is not separated, it is not isolated, it is already entangled with this one. And if this guy gets some kind of a change, okay, due to something, then this guy automatically gets changed. Okay, in fact, so there can be a phase. Okay, there can be a phase change, let's say. Okay, so the relative phases can, for I mean, just mathematically speaking, you can have a0 plus b1, which is, let's say, the psi state, and that can change to a0 minus b1. So here this bit is not flipped, but there is a change here. So there is a change in the relative phase here. It is minus now. Okay, so this is minus now. So there is change. So it can be thought of as some application of some sigma z. Okay, and that that has introduced.
It should depend on the state phi, right? So any kind of change is possible, isn't it, in decoherence?
Yeah, I mean, what I'm saying is, yeah, it is possible. I'm just giving an example. Like here, sigma z, suppose mathematically it can be said like suppose sigma z is applied on this, and I mean I can generalize it, but anyway, so this can happen, that there is a phase shift, and then we can call it, usually people call it phase shift error. I'm giving this examples because we want to talk about, let's say, how to rectify this kind of error if this kind of error happens. Okay. I mean, there can be many errors, but mathematically you have to model the error. Okay, so if there is a bit flip error, I mean, how many bits can be flipped? So we'll talk about that. And there can be a fetch shift error, and then the question will be how it can happen. And there can be combination of both also, like bit flip as well as phase shift. For example, like suppose you have this a0 plus b1, and let's say some action like sigma y had occurred here, and then this will be converted to I b0 plus I a1. So there is not only a phase shift, but there is also a bit flip. So it's a combination of so it is, I can say, just both phase shift error and bit flip error. Okay, bit flip error. So both can happen. So one of the primary goals in quantum computation is then how to rectify this kind of errors. Okay, so this is one of the motivations, like why we should talk about how to rectify error when you are performing some kind of quantum computation, and then this kind of error you can encounter this kind of errors, and then the question would be how do we rectify this kind of errors. Okay, and we are not in a classical domain, so then the idea will be, okay, I mean, how to rectify this kind of error. If we look back at the classical communication systems, okay, so then we will see that classically what happens is most of the procedures are basically, the key ingredient is redundancy. Meaning what? When you are doing this, if we want to work with some kind of, let's say, suppose, I mean, for a particular example, you can assume like, okay, suppose I want to send 0, okay, to some place. Okay, so let's say this is Alice and this is Bob. So Alice wants to send 0 to this Bob. Now, if this get flipped, okay, for example, there is something called a binary symmetric channel. Okay, if you know it. If you do not know, that is also fine. That is not a problem. I'm just giving an example. So I'm just trying to model mathematically what could be the possibility of error in a classical sense. So 0 can be processed or can be transmitted as 0, or 0 can also be transmitted as 1. And there could be a probability that 0 can be flipped to 1. So let's say the probability is epsilon. Okay, this is a crossover probability that 0 can be transmitted as 1 to Bob, and then it is 1 minus epsilon. Okay, so then 0 will be transmitted as 0. Similar thing, this also can happen. This is, let's say, 1 can be flipped to 0 with probability epsilon. This is epsilon. So this is a classical example, okay, of a channel which is called binary symmetric channel. Okay, binary symmetric channel. Why it is symmetric? Binary is of course okay, because we are transforming only, there are only two possible inputs, okay, 0 and 1. So So, and symmetric means here also you have epsilon, here also you have epsilon. Okay, so I mean, this is just a simple model. Okay, there can be this model of a channel. I mean, there can be different ways of modeling this. For example, another way is something called eraser channel, where you have 0, 1 here. But what could happen is, and there can be something which, let's say, some epsilon or some e. I'll tell you what e is. So let's say 0, and suppose you are sending, but suppose it get erased. Okay, so something you received, the Bob receives something, okay, which is doesn't know like what it is. Okay, so it is erased, let's say. It can happen also with probability some epsilon, and then also same thing could happen here as well. Okay, so it is not flipped, but it is erased due to something. Erased means it is something absurd is received. Okay, so this can also be, so this is called a classical eraser channel. Okay, so it is a channel. So since you have not done a quantum channel, I think, so it is not discussed. So quantum channel also, similar way, quantum channel also can be defined, but for understanding quantum channel, you need a little bit of advanced linear algebra, because quantum channel is nothing but a positive linear map. Okay, so you need to know a little bit advanced of linear. So that's why I'm trying to avoid this model of quantum channels. But the idea is why I'm discussing this is what happens in classically also. So then the question will be how to I mean, okay, so in order to set the context, let's say, why you are considering 0, 1, because anything in this world, I mean, it is according to Shannon that anything in this world, if you want to transmit, you have to digitalize this, and that can be, so there is a source. Okay, the source, whatever you want to send, let's say, whatever the message, audio, video, whatever it is. Okay, so the source can be so let's say you want to send some A1, B1, dot, dot, dots, or maybe A1, A2, dot, 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 some AK. These are the letters, source letters. Okay. You want to send, let's say, some, okay, it can be like in English letters like A, B up to Z. And then you have to digitalize this A1, A2, and AK. Then the question will be how to digitalize this. Then this is according to Shannon. And then A1 can be written in terms of some strings of 0, 1, A2 can be in terms of strings of 0, 1. Then what happens is you have to uh, uh, transmit it through a channel, not only one particular bit 0, but in fact a string of zeros. And if you want to send, for example, you want to send a combination of this A1, for example, if A1, A2, AK are like A, B up to Z, the English letters, okay, then suppose you want to send some information like, okay, suppose the word is information. Okay, so for I, there is a corresponding code or code word. There is a class N, there is some code word like string of 0, 1, and so for each of these letters. Okay, there is a string of 0, 1, and then you want to send it together. Then that means that's a big length. I mean, it's a block kind of a thing, block of strings of 0, 1s. Okay, and there will be also properties of the channel, like whether you can send that many, I mean, that much big length sequence or not. And if you want to rectify the error, so there is a possibility of error because it is a noisy channel. Okay, the channel is noisy. And then what you have to do basically is, okay, the classical idea is redundancy, meaning just whatever you want to send, let's say I want to send 0, 1, 0, suppose, through a noisy channel. Then the most important part here in classical error correction is that, or key, as I was saying, the key ingredient is like you just don't send 0, 1, 0, but put some ad hoc things. Let's say some zeros, let's say some 0, 0, 0, whatever, some extra binary digits you put, and that will help you to rectify if there is something is received. So that extra bits, these redundant bits, will actually help you to identify what is the, whether the received code word is erroneous or not. So here, so this is what is happening. I mean, what happens in classical error correction. Okay, classical coding theory. But we'll not discover. But this is just a brief review that this just to understand, like redundancy is very important here. Okay, redundancy is very important here. So you just don't, whatever you want to send. Let's say you want to send 0 to Bob. Okay, Alice wants to send 0 to Bob. So Alice should not say send only 0. So she should also transmit some ad hoc bits, let's say 0, 0 or 0, 0, 0, whatever. And then even if something flipped or all are flipped or at least one is flipped, okay, then there will be another procedure, let's say, okay, to identify what could be the error, okay, which bit is flipped possibly or not. Okay, there could be a mechanism to understand what is the possible possible error, or what is the change of about which particular bit is, let's say, flipped. Okay. So this is the idea in classical classical, let's say, error correction or classical coding theory. So we want to do the same thing here, which is in quantum also. So what is the idea? We want to use the concept of redundancy. So when you are trying to send something like, let's say, psi through a channel, okay, or somewhere, okay, want to perform some kind of, let's say this is 0 plus some beta 1, we just not only send psi, but along with psi, because I cannot copy it, so I'll also send some ad hoc bits and try to see what kind of model it is. Okay, how do I model that? Like, how do I introduce some other qubits here? Okay, and I can send it through the channel, and then probably I'll be able to rectify if there is a bit flip error, or there is a phase error, okay, phase shift error or not. Okay, so this is the idea. Now, before we go to that, so the question is here, for example, we have a probability of a bit flip is epsilon. Okay, this is the possible error. This is the probability of error is epsilon. Now, classically, if this is the way that redundancy, you use redundancy is the key ingredient. That means you also transmit some ad hoc bits. The question will be, how does it improve the error? Does it reduce the error? Improve in a sense, does it reduce the error? Can I get an error which will be less than epsilon? Then it will be good to do it, right? It will be convenient to do it. Otherwise, why should I do? So it should reduce. So when I'm saying this, redundancy is the way. That means it reduces the chance of error, and then only we'll be using it. Okay, and classically, it can be shown that most of the algorithms so people use, okay, or propose in the literature, they always calculate the error probability. Okay, like what is the probability that if you send something, okay, that error probability, that is the chance of error, and what will be that? Will it be, for example, in the case of binary symmetric channel here, the probability should be, the error probability should be less than epsilon. Then we will be happy to do it, let's say. Okay. So, and also this is another thing which we need to know about classical computation, because this is the thing which we'll be using in quantum computation, I mean quantum error correction. So the channels are different kind. Channels could be of completely different types in classical sense. Channel means something like binary symmetric channel. Okay, this is a noisy channel. But whenever we are sending this, so for example, this channel is called a memoryless channel. Okay, we call it a memoryless channel. What happens when, suppose I'm sending this string of 000, let's say, or whatever, 010, whatever. I mean, this is just an example. Okay. So the error in this particular bit, okay, what will happen should be independent of what happens here. Then it is called memoryless. Okay. So memoryless channel means whatever happens, the error happens to one particular bit in a string of bits. Okay, that will not influence error, or this will not affect in the error of any other bit. So this is called a memoryless channel, but channel need not be memoryless. Okay, this is an example of a channel which is, let's say, memoryless. Not memoryless channel is, for example, if you consider Markov channel. Okay, so that means if there is a bit flip here, let's say on the second digit, it may affect on the third one as well, and the third one, if there is an error, that may affect on the fourth one as well, and so on. So, and there are other channels, for example, stationary channels. There are other models of channels, but let us assume that this is a memoryless channel. So memoryless channel means what then? If you are transmitting 000, let's say, and let's say we have a binary symmetric channel, that means that the crossover probability that 0 will be flipped to 0 or to 1, or 1 will flip to 0 is epsilon. Okay, and without error, the transition probability is, let's say, 1 minus epsilon. These are also called transition probabilities, by the way. These probabilities, these are also called transition probabilities. Okay, so epsilon is basically bigger than 0. So if it is epsilon is 0, so there is no error. So this is not a noisy channel in that case. Transmission probabilities. Okay. So then what happens is, suppose you send 000, but this is Alice. Alice is sending 000, and Bob receives something. Okay, what Bob could receive? Bob could receive all possible, let's say 01000 or 0010, okay, 110, anything. It can receive anything, because let's say this channel is noisy, and then there is a chance. Now then our question will be, what is the probability that if Alice sends 000, what is the probability that Bob will also receive 000? So here that can be computed, because this channel is memoryless, because 0, if Alice sends 0, then Bob will receive also 0. That this will happen with probability 1 minus epsilon, right? So that means, and this is independent of that, so the probability will get multiplied. So the probability will be 1 minus epsilon cube, let's say. Okay. Similarly, if Bob receives 010, what is the probability? This will be epsilon into 1 minus epsilon square. And this will be 1 epsilon squared times 1 minus epsilon, and so on. So it will be like epsilon cube, and so on. So there is a probability, okay, associated with all these things. And now see, in all the cases, these are the error. These are the error probabilities. These are reduced now. These are all less than epsilon. These are all less than epsilon. Okay, so Bob receives something which may be erroneous thing, but the error probability reduced from epsilon. These are all less than epsilon, because 1 minus epsilon is, let's say, positive. Okay, because epsilon is, let's say, positive. So, and this is less than 1. So these are all, so error probability is actually reduced when you send extra bits. Okay, so this is, as I wanted to show you, that it always reduced. Okay, so the error probability
not always, right? Because epsilon times 1 minus epsilon square can be more than 1 minus epsilon cube, right?
No, I'm saying that less than epsilon. What I'm saying is less than epsilon.
Okay, yes.
Okay. So the thing is that okay, suppose Bob understood, like, okay, there is an error, okay, and let's say there is one bit error, okay. So I mean, it could be 2 bits error, also 3 bits error, also depending on whatever length, whatever the length of the string is, or Alice is sending, let's say. So that could be 1 bit error, 2 bit error. So now, depending, you can define different kinds of mechanism to rectify, let's say, 1 bit. If there is 1 bit error, then possibly you can rectify. Then there are models where you can rectify, let's say, 2 bit flip error. I mean, we are assuming, let's say, it is binary symmetric channel, so there is only bit flip error. Okay, like 1 can be changed to 0, or 0 can be changed to 1. So there is only this kind of a possibility is there. And so this is what is happening. Okay. Now the thing is, yeah, what I was talking about. Yeah. So then what is the mechanism? So one mechanism is like for correcting let's say this one bit error is something called a majority voting. Majority voting. Okay. So suppose Alice is sending these 3 bits, okay, and Bob receives something, and there is Bob receives, let's say, 010, the 1 bit flip change, okay. Then what Bob will assume, whether because majority means this majority is 0, so Bob will assume, okay, this probably has changed from 0 to 1, so this should be treated as 000. So this is now rectified. So this is one way to do it. I mean, there are many ways to do it. We'll talk about that.
So this will work only if epsilon is less than half, right?
Yes. Epsilon is less than half. Yes. Epsilon is less than half. Yeah, that's true. So I forgot to mention that. Yeah. So 0, 0. I mean, otherwise it will increase, but it will perfectly. I mean, it will perfectly work. I mean, it will always decrease. Let's say epsilon is less than half. That you can show. Yeah. So 0, 0, 0 to 0, 1, 0. Suppose Bob has received this one, and Bob applies this majority voting, and then what happens is Bob can rectify 1 bit error. If only 1 bit is flipped, then Bob can always use majority voting and can detect the error if there is only 1 bit flip error, but need not be 1 bit always. Okay, but suppose there is only 1 bit flip. Okay, so only one single error happened. Okay, then Bob can identify that error, rectify that error, let's say, using majority voting. That most of these are, let's say, 0, or most of these are 1. Okay, so the remaining part, whatever, I mean, it could be, need not be 0, 0, 0, but something, let's say 0, 1, 0, or whatever it is. Okay, whatever it is. And then suppose Bob understood that, okay, so he received something like 0, 0, 0. Okay, so then what will happen? 0, 0, 0. So majority is 0. So Bob may understood that, okay, so 0 probably had been sent. Okay, so he may also, need not rectify always the error, but there is a chance. For example, here, if there is only one bit flip error, that can identify. Okay, but here there is only one bit flip error, but this need not, this majority voting need not always rectify the error, but this is the way to do it. Okay, this is the way to do it when you are sending a large number of bits, and let's say there is only one kind of a bit flip happened, and the Bob will count whether number of zeros are there or number of ones are there, and probably then there is a bit flip error, and Bob probably can rectify it. And this is a way to do it, majority voting. Okay, and in fact, in a quantum setup, whatever I will be discussing, we'll use this majority voting. Although this is a silly way of doing it, but anyway, I mean, there are other ways of doing it in classically. Okay, but we are not discussing here classical computation. But anyway, so this is one way to do it for a one bit flip error. Okay, so yeah, so so then what we can say? I think now, yeah, so maybe now we can talk about the first quantum protocol, let's say, or for rectifying, okay, a bit flip error for a 3-qubit bit flip code. Okay, so this is called a 3-qubit bit flip. So this is one procedure or one code, how to detect error and how to rectify error. So what is happening here? There is Alice. So this is one particular example of a coding technique. Okay, so how to rectify, how to send, let's say psi. So Alice wants to send Bob a state which is psi. Okay, but there is a chance of error. Okay, it may be flip, let's say a bit flip, and then so there is this noise is due to bit flip. Okay, bit flip, and Bob can receive something else instead of psi. And the question is, I need to rectify that when there is a bit flip error. Okay, so how, what should be a way to do this? Okay, so what should be the protocol? Okay, so in this particular protocol, okay, what Alice does is, let's say, Alice does this kind of an encoding. So for 0, instead of 0 qubit, okay, so Alice encodes this into, let's say, a logical bit corresponding to this, which we will write 0L. That's why it is called 3-bit, a 3-qubit. So instead of 0, she wants to make it 0, 0, 0. Okay, I'll tell you why did I say she wants to make it 0. I'll tell you that. And then there is for the 1, she has to encode it, let's say, using 1L. The logical L stands for logical. Okay, logical bit. Or just the code word. This can also be called a code word. So some people write or call it logical bit, but I think communication people always call it code word. So, and Alice wants to code this 1 bit, 1 qubit as 1, 1, 1. Okay, so instead of 1 qubit, she wants to encode it using 3 qubits. Okay, so what happens then? If she can do that, then if she wants to send psi, which is alpha 0 plus beta 1, she must produce this state using some local computation, let's say. Okay, she has to produce alpha 0L plus beta 1L. This is the technique. This is the first thing she has to do. So in order to protect it from a 1-bit flip error, okay, so this is alpha 0, 0, 0 plus beta 1, 1, 1. Then the question will be, how can Alice prepare from this to this? Now say here, I cannot use any kind of a measurement because I cannot destroy this state. Without destroying it, I want to encode it here. I want to produce this state without destroying the psi. Okay, I want to encode this psi in a new state. Let's say this is psi tilde, okay, without disturbing psi. I
You
cannot
can
disturb
use
in
C
second.
naught gates, right?
Yeah,
C naught.
yeah. So yeah. So I'll tell you the circuit, what Alice can probably do, or you can tell me the circuit. Can you tell me the circuit? How
Yes.
still
We
produce this?
use.
Yeah.
We can put ancilla 0, and
Yeah.
from psi we take a C naught to that ancilla 0. We
Mm-hmm.
take two ancilla 0 and two C naughts like that.
Yeah. Okay. Yeah, that is what exactly Alice can do. So there are two ancillous qubits which Alice can consider, and this is, let's say, psi. And what she does is first use a C naught here and then C naught here. Okay, then so this will be psi tilde. Okay, so this entire state is psi tilde now. This is the output of this quantum circuit. So this is the, let's say, the quantum circuit, the circuit which realizes this particular operation, encoding technique. Okay, and you can see that this is this psi tilde. I mean, you always have to check whether we are doing something which is fundamentally wrong. That means it is, I mean, you need to check that this is not this. We are not producing copy of this. Okay. Whatever. So I mean, we are not using any copy of this. Okay. So it is not psi times psi. Okay. We are not doing this. Okay. This is not equal. Okay. So we are not disturbing this or not producing a copy of this
So we
because
can't do that, right?
we cannot do that. Yeah, because we do not know what psi is. Basically, we do not know what alpha beta are. So without disturbing alpha, so that's why I'm saying without disturbing psi, I still can produce this. Okay, so this is the most interesting part. And this is actually a very famous state. It is known as Z state. Okay, so this is Greenberger, Horn, Zellinger state, or some people also call it a cat state. So this is a 3-qubit GHZ or GHZ state. So there is also a 5-qubit GHZ state. We'll talk about that probably, okay, later on. So this is the state what first Alice will do, encode this bits. Okay. Now what happens? So Alice now passing this or transmitting this state psi tilde, okay, through a noisy channel. Okay. Then there could be a bit flip error when Bob receives that, right? Now what Bob could receive, possibly. So my psi tilde, this is what Alice sends. This is alpha 000 plus beta 111. Okay. Now let us say, I mean, we have to consider some kind of error. Okay. So let us assume that a bit flip here, bit flip means the qubit. Okay, bit flip. I'll tell you what is that. Maybe we can write it sigma z. Okay, bit flip error can happen. Let's say due to the noisy channel can happen. Okay, with probability epsilon. This is the error. Okay, with probability epsilon. So now so then okay, so if it is epsilon, so then 1 minus epsilon is that like the qubit is unchanged, like 0 will go to 0 and 1 will go to 1. Okay. So now if Alice sends the psi, so Bob receives something else. Okay, that could happen. Okay, so Bob may receive just the same thing, 000 plus the beta 111, and then we want to see what is the probability. Okay, so I mean we just want to check whether the probability, okay, error is less than epsilon or not. So what will the probability? This will be the same thing because this Bob sent a alpha. This 0 is not changed. This 1 not changed. This is not changed. Right? The first bit is not changed. Second bit
1
is not
minus
changed. Yeah. So it is 1 minus
epsilon or
epsilon.
3.
Yeah. And similarly, Bob can receive probably 100. Maybe the first bit Okay, first qubit is changed. Okay, so if first field, so you are basically this change can be measured by sigma x. I mean, this can model as sigma x. So you are acting sigma x on the first qubit. Okay, so here if you apply sigma, I mean, this is like acting sigma x on psi star, psi tilde. Okay, so sigma x, I mean, sigma x means here sigma x I times I. Okay, so that means this sigma x is acting only on the first qubit. So if it acts that, so that's why it is 0 is changed to 1. I mean, this was the original state, psi tilde. So this is what Bob received. So that's why I'm writing this. And this 1 is changed to 0. Okay, so there is only one primitive. So this is with probability epsilon times 1 minus epsilon whole square. Then another thing what can happen is Bob can receive, I mean, you can write the Norse possibilities plus beta 101, and this will happen probably 1 epsilon square and so on. So you can just check again that if epsilon is less than half, then the error probability is less than the error probability epsilon. Okay, so this is so that means we can reduce the error probability just by sending this. Then the question will be, if there is a bit flip error happen, okay, then how to rectify that? How does Bob, okay, rectify this? Now, what Bob can possibly do? Okay, now if Bob can perform some kind of measurement, okay, this is what Bob can do possibly, or can use a circuit, okay, for which this received state is an input. Okay, so Bob can apply a quantum circuit and use this received, let's say whatever psi tilde, or maybe, okay, so how do I denote it? Okay, I may write this as Alice and this as Bob. Okay, this is Bob received, this is Alice, and psi, I mean, this will be better maybe. Yeah, so this is alpha 000 plus beta 111. Now Bob receives something, so Bob can do two things. Okay, either so Bob can either perform to rectify the error, let's say, either one bit flip error. Bob can either perform a measurement, or the received one as an input for another circuit, as an input for another circuit, and then he designs the circuit in such a way that this one bit flip error, if there is one bit flip error, that must be rectified. Okay, and Bob should receive the original one. Okay, so an input, or you can use this as an input for another circuit. Okay, this is what Bob can do. Now say here what Bob can possibly do. Bob can measure, there are 3 qubits. Bob can measure each of them, okay, using some, let's say, sigma z. Okay, something Bob can, let's say it is like polarizations. Okay, so then Bob can measure using around the z axis, let's say. So Bob can measure this, I mean, using something he can measure this, let's say. So I'm just giving an example. Let's say Bob can measure the first qubit, second qubit, and third qubit, some this. But if Bob does that, that will change the state. So Bob will not be able to receive the state, because once he does the measurement, this state is now changed. So he actually did not receive anything. Okay, so the superposition of the phi, this once Bob this perform a measurement, okay, whatever it receives, now there is a superposition, but once this is a measurement, the superposition will be destroyed. So Bob actually cannot measure anything for the time being. So Bob cannot measure any individual qubit. If Bob measures an individual qubit, then the superposition would be lost. Okay. So, or you can say that Bob measures with respect to your computational basis. So either Bob will receive whatever, this one, or let's say this one. So there is no superposition anymore. So Bob cannot do this. Okay. Now, what Bob possibly can do, okay, is the following. Okay. I mean, I'm just giving an example. From that, probably I'll talk about, okay, what is the theory behind it? Okay. Suppose, okay, let's say, suppose Bob receives something. It receives, okay, it receives, let's say, some alpha 1. So this is actually the psi b, let's say. Bob doesn't know that, okay, but let us see. Suppose this is an example of such state. Plus b, let's say 0, 1, 1. Okay. Now what Bob does is he uses a new circuit and use this as an input. Use this as an input for that circuit. Okay. So what he does is he uses this kind of a circuit with some two ancillary qubits. Okay, so this is the thing. So this is the input here. Let's say this is psi b. Okay, and then uses two bits, two qubits, add of qubits. One is at 0, one is at 0. So this is an all-known protocol. Okay, so now Bob, what he does is he applies this here. We'll see the effect of this. Okay, and then here, and then here. And then here, and then there is some kind of a detector here. Let's say some D1 or D0, D1 kind of measurement. Okay, Bob does. Bob is not doing anything on the received one, but he wants to rectify this. Okay, using performing a measurement on the act or ad hoc on the ancillary qubits. Okay, and Bob will obtain something, some x0. This is classical information, some x1. Okay. Now, so now first question is, I mean, how does it do it? So, why? What is the use of this circuit? Okay, and what are these D0, D1, and what are these X1, X0? That I will be explaining now. So, if Bob uses this 4 C0 gates, okay, so let's say this is one, the first one, this is second one, this is third one, this is fourth one. So, Bob does that to the psi b, then what will happen for this input? So, my input state for this entire quantum circuit is psi b times 0, 0. But psi b is what? Psi b is alpha 100 plus beta 0, 0, 1, 1. Right? Yeah. And then we have this 0, 0. So actually, this is a 5 qubit state now. Alpha 10000 plus beta 01100. Now, when the first gate is applied, so first gate is what? This is C0 gate, and this will act on this particular input if the first qubit is 1. So if you do that, this will act only on this part. Only on this part. It will act only on this part. So if we apply 1, so then this will be changed to this bit will change. So the fourth bit. So 1, 0, 0, 4 bit 0. Okay, and this will remain invariant 0, 1, 1, 0, 0. Now, if we when Bob applies the second NOT gate, so this will act when second qubit is 1. So that means here it will act second one, and then it will act on the fourth one. So it is like alpha 10010 plus beta 011, and fourth one is 1. Now again, third one is again first one is 1. The third one, and it will change the fifth one. Okay, so the third one, so then it will again change this one. So alpha 10011 plus beta, and it is the same. Now Bob will apply the fourth one in the circuit, and it is the third one is 1. So it will only act here. So alpha 10011 plus beta 01111. So now you can see that this is alpha 100 plus beta 0 1 1 times 1 1. Okay, so here 1 1. So that means, okay, so this one you can write again some alpha 1 0 0 plus beta.
Can you just once show the circuit?
Yeah.
Okay.
Okay. Yeah. So Bob will get this times 1 times 1. So this is actually the first ancillary qubit, and this is the state of the second ancillary qubit. Now Bob wants to perform a measurement on this qubit. Okay, and Bob will get two values. Either Bob will get 0 or Bob will get 1. Okay, depend. See here, the circuit I used. If this is my input, this is I already have considered an example. It is not a general qubit. Okay, and this is not need not be that Bob has received this. I'm just giving an example. So if Bob has received this, then this is the qubit. This is the state for the first ancillary qubit, and this is the state for the second ancillary qubit. Okay. Now Bob can perform a measurement on the first ancillary as well as on the second ancillary, and Bob will get either 0 or 1. So what I'm saying here is x0, x0. So this is kind of a measurement, kind of a detector. Okay. So I mean, if you have done this can be also called as a measurement. Okay, it's kind of a measurement. So then x0 and x1. Okay, can be either 0 or can be 1. So these are the classical bits. So now, so upon measurement, okay, Bob gets, okay, two classical bits. Let's say either so let's say x0 and x1. Okay, and this x1 and x0, these are called error syndrome. So errors, I'm not defining what is error syndrome in a classical sense, but here, in classical sense, for example, if you have a linear block, okay, let us forget about that. Okay, so it will take a time. It will take a little time. But yeah, so here in the quantum setup, let's say, let us assume. I mean, this is what I'm trying to tell you is that this is not a term which is very new in the theory of coding. Okay, so or error correcting coding or error correction coding. So this is error syndrome x0 and x1. Now suppose, so here what happens is if Bob measures x0, Bob measures the first ancillary qubit, so the value of x0 will be equal to 1 and value of x1 is also equal to 1. Now what Bob decides is if x0 equal to 1, suppose Bob concludes that one of the first two qubits has been flipped. So Bob is doing something here. Okay, he's deciding something here. I'll tell you the general principle, but before that, let me say that Bob decides the following. How Bob rectifies the error. This is what I'm saying. Bob decides the following: that if or since, let's say Bob decides since x not equal to 1, okay, one of the first two qubits, okay, has been flipped or changed or flipped, okay, and since x1 is equal to 1, suppose Bob decides that either first or third, okay, qubit has been flipped. Suppose Bob decides like this. Okay, so Bob decides, okay, if I get x not equal to 1, then one of the first two bits is flipped, and if x1 equal to 1, then for the second ancillary qubit, he decides, okay, then either the third one or the first one has been flipped. He has to decide a mechanism, but I'm just giving an example. Okay, now if both are happening, that means what? first two, and this is first and third. Now definitely Bob is now sure that actually both are happening. That means the first blip hasn't flipped. Now let us check whether first blip is changed or not. Okay,
So that
so
is if we think that only one bit is flipping, right? If
what? Yeah. So I'm talking about only one bit flip correction. Yeah. Only one bit flip correction. Okay. Yeah,
but
one
but
bit is
we,
only
we will
flipped. So
not know how many bits are flipping, right, when we pass through the
no, no,
channel.
no, 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 no. I'm assuming that suppose there is only one bit flip, that can be decided or not. That can be detected and rectified or not.
Yes. Okay.
Okay, so this is the protocol for correcting only one bit flip error. Okay,
Yes.
so yeah, and this is actually the first one in the literature.
Okay.
So maybe one of the first ones. Okay, so since so then Bob decides. Okay, so then Bob found out. Let's say Bob decides like this. So there is a mechanism to choose which one. Then there could be questions like what happens if x not equal to 0, x not equal to 1, or some other values of x naught and x1. What will happen? Okay, I'll give you the complete picture. But suppose if this equal to 1, then either first two, and this is 1, then either first or the third. So from this, since both are 1, Bob decides, oh, okay, so then the first one hasn't flipped. So then what Bob will do? Bob, in order to rectify, Bob will apply sigma x, the NOT gate, on the first qubit. So this is my received one. What is the received one? So this was psi, let's say B, and this was what? Here we assumed that this was this one, right? So there is only one bit flip error in the first one. So Bob detected that based on the observation or based on the measurement on the ancillary qubits. Okay, so then Bob will apply. Okay, this was my alpha 100 plus beta 011. Then Bob will apply sigma x on the first one. So he's not disturbing anything on the received qubit, you see, a received state. Okay, so he's only change everything Bob is doing on the ancillary, not changing the psi. So if he does that, then Bob receives this 000 plus beta 111. So Bob rectifies the state and got the desired state. Okay, now the question is, what is the general protocol? Okay, so how does Bob choose this and what is happen? What will happen? So here the recipe is the following, that if Bob decides the following, that if x not equal to 0, x1 equal to 0, no action. Bob will not do anything. So he will assume that whatever he has received, this is correct. If x naught is equal to 0 and x1 is equal to 1, he'll apply not gate, apply not a sigma x to the third qubit. And if x naught equal to 1, x1 equal to 0, then apply not on the second. And both are 1, apply not on the first. So he does not do anything, but he designed the circuit, okay, in such a way, the reverse circuit actually. Okay, so I'll tell you like this. So once you get this, okay, so where is that? Yeah. Yeah. So what Bob does is basically he designs a circuit like this. Let me just draw it first. This is the error correction circuit. This will be this one. This will be this one. And he will apply here What's that? Okay, so first on this. So apply the first one. Okay, only when. So here is, let's say, my table. Okay, as a display, let's say, whether x naught is equal to 0, x1 equal to 0, x naught equal to 0, x1 equal to 1, x naught equal to 1, x1 equal to 0. I mean, there are difficult, I mean, there are many fancy way of drawing the circuit, but let me do it like this way. So if both are 1, then Bob apply this. Okay. If this is 1, this is 0, Bob applies on this one. If this happens, Bob applies on this one. And if the other thing this happens, Bob does not do anything. Okay.
Can you realize this function, this box computationally in quantum? It's like
This box?
yes, sir.
Yes, yes. It is a measurement.
Demultiplexer.
No. Yes. So you will get one of these option, either this or this or this or this. So
Yes.
what happens is, once you measure this, right? So I think he probably, Professor Majumdar probably has talked. I mean, he might have talked about it. So that you have a Hadamard, right? So let's say, I mean, kind of a gate, or kind of some kind of a beam. Let's say where something is coming here, and then there is this way and this way, right? So the perpendicular something what is called I forgot the term. Beam splitter, right? This is the splitter.
Yes, yes.
So yeah. So using that, so you can see whether it is going this direction or this direction. So it is, let's say, 0, okay, and this is 1. So you can automatically get the value. So what is the state here? Either it is 0 or 1. So you can measure once you measure this.
So measurement is fine, sir. But after measuring, how do we? So this is like a demultiplexer in classically, but so classically we can realize using AND gates and OR gates.
Here. Yeah, here we are doing this. Now, once you see the values, now here is the circuit. This circuit I have drawn. Because I have to apply, so whatever the first one, second one, third one, based on this, I have to apply this on some NOT gate here, either here or whatever the value of x1.
Okay, from here we can do classically, you are saying.
Yeah. No, not classically. Based on this value, x1 and x0, I'll switch on and switch off, let's say. I mean, this is very ad hoc what I'm saying.
Yes,
okay,
yes, these are x0 and x1 separately, right? And now these two outputs, x0, x1, you are demultiplexing into 4 different kind of outputs, right? x0, x1 equals 0, 1, 2, and 3. So that how
I mean, one of this will happen, right? Yeah, one of this will happen. So either x0, suppose you got x1, x2, both are 1. Then what you will do? You will apply this on the first bit. So you'll this NOT gate on the first one. Okay.
Yes. So how will you decide that then if x0 equal to 1, x1 equal to that thing? So that condition.
This is the protocol. If you do this, this is the recipe. This is the theoretical result. If you do that, then you can always rectify the error. That is what I'm saying. You can prove this theoretically.
Yeah, yes, sir. I agree. We can rectify the error, but but is there a way that there is this logic, right? This recipe itself. If x0 equals 0, x1 equal to 0, you don't do any action. If x0 equal to 0, x1 equal to 1, you do some action. So is there for that? Is there a circuit?
No. So if this, then it will so I think if I understood your question correctly, if this is this one, then how it is automatically, so you want to do some automation.
Yes.
So automatically this will be switched on, switched off. I think this will be, I mean, I don't know that, frankly speaking, but this can be done probably, yeah. Because recently we have done some work. Okay, so I mean, so this work is like, I mean, there was a student, Siddhant, who was doing project with me. Like, so he was integrated MSc student physics. So he did his project with me, and in his project, what we did is Yeah, so we introduced a formula using superconducting qubits. So as I said, there are different kinds of platforms. So we said, okay, so I mean our okay, let me just say it like this way. So suppose we have this a configuration of a hypercube. It could be anything. Okay, I'm just giving a picture 2 to the power 3, but it could be 2 to the power n as well. So this circuit, suppose I want to find a square inside it and to design a square inside it. So if I want to, so these are all qubits, by the way. Okay, these are all qubits sitting here. Okay, so then we propose the setup, experimental setup. I mean, why I'm telling you that this is possible? That suppose I'm doing this, like I want to find a square, let's say. I mean, in fact, the protocol is like this. I give you any two vertices, okay, of this hypercube. This could be any dimensional, n dimensional. This is 2-dimensional, 3-dimensional, okay, but it can be n dimensional. The protocol is like this. I give you two vertices in the n dimensional hypercube. Then you have to give me a hypercube for which those two vertices are antipodal. For example, if I give you this one and this one, okay, then the question will be, what is the hypercube for which this is antipodal? Or maybe antipodal in a sense, okay, like, I mean, let's say if you just label this 0, 0, 0, 0, 1, 0, and so on, I mean, the
Like they are
labeling of this,
diagonals.
yeah, so anti meaning this is completely, this two vertices are the complement of other, okay?
Okay.
Okay, complement of this. So this is the problem. So, and this we propose a protocol, I mean, realization in terms of experimental setup, where we can switch off and switch on this connection so that we not only it realizes, but we can work on that particular square. Let us say we do this one. Let us say, for the example, okay, let us say that we realizes this one. That then what it'll do is it will switch off this switch off these connections. Okay, so this will switch off these connections, and you can work with this one. I mean, the
Okay.
work we
Yes.
propose is
Nice.
perfect state transfer. So this can be done. Okay, so this can be done. So you can
Okay.
see this paper. So this is published. This paper is, you can see in my webpage. It is there. It's called perfect state. The title of the paper is, I think, perfect state transfer in hypercube using superconducting qubits, something like that. That's the title of the paper. Okay, so I think it is possible. It is not a big deal because once you have this, you can switch on, switch off some of the things. I mean, see, this is just an icon. It is not a realization. Okay, this is just an icon. Circuit is not like this. There is no wire, although these are look like wires. Okay, there's a classical, inspired by the classical icons, but there is nothing like this. There is no wire here. So it has to be implemented in a completely different way. But we need a mathematical representation of what is going on. And that's why we have this kind of a picture. Otherwise, there is no role of this kind of picture here in the quantum circuit. Okay, I mean, there is no wire there, let's say. I mean, these interactions are completely realized in a different way. But for visual representation, we're using these icons. Okay. So anyway, so this is the recipe, and this can always, you can check, like deciding all this different kinds of what is called SIB. Okay, this is one kind of SIB, so you can do that. What is happening is, so this behind this recipe, the logic is, Bob is not, I mean, the origin of this protocol is that Bob is not measuring the qubits individually. This, I mean, what is the effect of this ancillary qubits? So what is the circuit here? Bob is not actually measuring this individual qubits, but what he is doing is he is doing collective measurements of two qubits simultaneously, and which is realized, the measurement result is realized by measurement of these ancillary qubits. This is what happens. So for example, Bob can do a perfect measurement here and here, but Bob is not doing that. But this is realized by measuring this first ancilla. And when he's doing, let's say, first and first two, then it's realized by X naught. And when he's doing, let's say, first and the third one, okay, then it is realized, so that result is realized by X1. Okay, so this is what is happening inside. I mean, if you read the story, so this is actually what is happening by this. I mean, so I mean, if we write it this way, so then, so Bob is performing. So the inside story is like Bob is performing, but not exactly performing. Okay, the performance result, the measurement result is obtained by measuring this ancilla qubits. Okay, but the inside math is like as if he is measuring the first the pair of the 3 qubits, and the whatever he's supposed to get, either he's what are the things was he's okay. I mean, let me just see. Bob is performing what he's performing, measuring what. Okay, we always measure an observable, right? Performing a collective measurement, collective measurements on 2 qubits simultaneously, and one is, let's say, sigma z 1 and 2, so first qubit and the second qubit. So this is a tensor product basically, and another is sigma 1 sigma z 3, first one and the third one. And what it does is that when you apply all the C0 gate and this and that, whatever you do that, so after, so measurement means you will get, if this is observable, let's say. So when you are measuring that, you can multiply identity also here, so that it is 2 to the power 3 by 2 to the power 3. So once you measure, so the eigenvalues of this are nothing but +1 -1. You can check that because it is a tensor product of a matrix, like or let's say Kronecker product. You can just see. So eigenvalues of A, B, C, this product is nothing but, I mean, let's say, let me say this. I mean, this is basic, but just suppose I want to, so A and B are matrices, then what are the eigenvalues? Eigenvalues will be the values after, I mean, you get after the measurement, right? So A and B, then eigenvalues of this are nothing but eigenvalues of this times eigenvalue of this. Here you have sigma z and identity. So then eigenvalue of sigma z is +-1, eigenvalue of sigma z is +-1, eigenvalue of I is 1. So if you multiply, actually you are supposed to get either +1 or -1. Similarly here as well, either you are supposed to get +1 and -1. Now this +1 and -1, either you will get this or the. Now there is a correspondence between x0 and +1 and -1. So if x0 is equal to 1, or let's say x0 equal to 0, then this, if this, it corresponds to, so I'm not going to the detailed proofs, corresponding to the value that after measuring this, you are actually supposed to get. I think I got disconnected, right? Can you hear me, guys?
Yes, now
Yes, sir.
Okay, so yeah, so time is up. I mean, what happens is I exactly have to follow that time because I need to make certain calls, right? So what is happening? Why it is? Can you see the screen?
No, sir.
Oh, I cannot. Yeah, I think you can see the screen, right?
No, yes.
Yeah. So, oh, recording. Did not stop. Okay. Oh, okay. Just a minute. So the inside story, what I was telling you, is that yeah, when x not is equal to 0, this is what I said, x not equal to 0, then it will correspond to the fact that sigma z1, sigma z2, value of this after measurement should be equal to 1. And when x not is equal to 1, then corresponding to this, the value of, if you measure this first and the second qubit simultaneously, then you are supposed to get -1. Similarly, if you get x not 1 is 0, then this will be 1, and like as if you are measuring the first and third qubit, and that will give you value 1. I mean, this can be checked. This can be checked. Okay, you can do the mathematics and can check. This can be checked. And otherwise, yeah, if x1 equal to 1, then you can see that sigma z1, I mean, if you measure first and the third qubits, then you are supposed to get actually -1. So this is the inside story. But even if you don't know this, still you can just check, because there are only few 1-bit flip error here. So
Can
you
you say
can
what
check
sigma
different.
z1 is?
What?
What
One?
is sigma z1?
Sigma z1 means I'm applying sigma z on the first qubit. And sigma z2, let's say I'm applying sigma z on the second qubit.
It's an operator, is
So
it?
I want to perform this. Yes. Sigma is the gate, no, Pauli operator gate. Okay.
Yes. So
Yeah.
yeah, do you mean sigma
Yeah.
x because bit flip is happening, right?
No. Sigma z, you have eigenvalues 1 or -1. Sigma z is this one.
Oh, okay, right. Yes.
Yeah, so you will have this. So basically, this is the standard basis. Your eigenvectors are like 0. So you are measuring with respect to this computational basis, basically 0 and
Yeah.
0 and 1. Okay, so yeah, so you are measuring this simultaneously, first and the second one, and first and the third one. Then you will see that this math works. Like when x naught, I mean, how the x values of x naught and x1 will decide what to do, right? How does it decide the recipe? How can somebody come up with this particular recipe that you have to do
So
this?
sigma
So there
z1
is
into sigma z2 is the measurement outcome of sigma z1 and sigma z2, right?
so this is the observable which you are measuring, and then you will get one of the eigenvalues as an output, right? You measure an observable, right? And then
Right.
you get, yeah, so and then you get an eigenvalue as an outcome, right? So this is what
Okay.
you are
Yeah.
doing.
Right.
Other way of saying it, yeah. So other way of saying it, that instead of saying observable and this and that, you can just say, okay, you are measuring in a basis which are actually nothing but the eigenvectors of that observable, right? Because after
The observable
measurement,
is sigma z1 tensor sigma z2 tensor I.
I
Or okay.
yeah. So yeah. So if you do that, then you see that this is how the math works, and so that's how one can come up this kind of a recipe, that if this happens, then do this, and then otherwise, what you can do is like you can just check different psi. Okay, one, because you are only correcting only one bit flip error, so you know all possible deviations. Okay, because this was the intended one, like this one is the intended one, psi b, psi a. Okay, this is what Bob receives. So psi a is the intended one. So this is, I think, yeah, this one. So it's the intended one. So if you just give one bit flip error and then see, suppose Bob receives something, and then we apply this rule of x0 and x1, you always get this. So yeah, so then we can, using this code, okay, we can rectify one bit flip error. Okay, so it can identify and rectify one bit flip error, and the probability of error is also reduced because we use 3 qubit. Okay, instead of 1 qubit, sending 1 qubit, you send 3 qubits, some ad hoc qubits, and then that reduces the probability of error. Of course, the value of epsilon is less than half, and then it, yeah, so it works. This method, this protocol works. And yeah, so maybe next day we'll talk about some kind of phase flip code. So this is what is called bit flip code, and then using 3 qubit. So, and then possibly we'll talk about other codes next day. Yeah. Okay, guys. Oh, I think yeah. Next Monday. Today is what? Today is I think. What is it today? Today is Tuesday, right? Yeah, I think next